Hello.
Okay. Everybody has their tiles cut out?
Yep, I got my tiles cut out.
Good. Okay. So have you started putting together your compounds?
I have not.
Okay. So you're going to want to do that?
So you just want us to tape them together or what?
Yeah, you could tape them together, or you could, like, you see where the holes are at? Some people actually just put little strings to connect it. You know, people were creative.
So we just put them together off of the thing on the lab, right? On the actual lab, it shows what we're putting together.
Yep.
Okay.
Pretty straightforward, right?
Should we have our cameras on the entire time, even when we're just cutting?
No, you don't need to have it on the entire time. Just
Wait, so Dr. Henry, are we only doing the models for number 2?
Yep.
So just for those 5 molecules, basically?
Yeah.
Okay.
For the supplies that we need, Dr. Henry, do we need tape only?
You can use tape, that'll be fine, or you can use a clip or like paper clips and stuff like that.
Okay then. Let me go get tape and let's see what's the best option for me.
Yep. Okay. So real quick, let me see if I can share my screen. Can you guys see it? See the lab?
Yes.
Yes.
Okay, good. Okay, so if you look at it, it kind of gives you the instructions. So we've talked about who's going to be the center atom. I show you a quick way of doing it. And then I'm going to show you on Thursday the more defined way of doing it. You want to make sure that you count the number of valence electrons, make sure you have the appropriate amount of dots. So if you guys take a look, so the dot that's filled in, here's my nitrogen. The dark dots represent the valence electrons, the white dots represents the space. So technically hydrogen should have 1 dark dot and 1 white dot. Yours only have a single dot. I'll have to fix that. Okay. So I'm going to write on my screen. So we did ammonia, which is NH, H with a lone pair. Okay. Oops. Okay. You guys see can you see the ammonia on my screen?
Yes.
Okay, good. Valerie, can you see that ammonia?
Yes.
Okay. So when we're talking about these molecules, they're going to have 3-dimensional space associated with them. They're going to have what we call geometry. Okay. The way that we determine geometry is by the number. It's called the Vesper theory, right? It stands for valence shell electron pair repulsion theory. Okay, Vesper. Okay. Now, the way it works is real simple. The simplest way, you want to talk about the number of attachments it has, right? We have what we call the electron pair geometry, EPG. Electron pair geometry means that you count everything that's attached to the center atom and lone pairs, okay? So in this case, we have 1, 2, 3, 4 things that are attached to it. So it's electron pair geometry, means there's 4 attachments. Anytime that there's 4 attachments to it, it's going to be tetrahedral. You're going to ask me, what is tetrahedral? I'll answer that.
What is tetrahedral?
Okay. A tetrahedral is a geometry. Have you guys ever played with jacks as a kid?
Yes.
Little.
Yes. Okay. So a jack has 4 sides, right? So you have the center. The center represents that center atom. In the case of a jack, you guys see my glow sticks? Okay. So my hand represents the center atom. The end of the glow sticks represents an attachment. So it has 4 attachments. 1, 2, 3, 4, not including my arm. Okay. So each glow stick represents an attachment to the center atom. My hand is the center atom. Okay. Now, if you look at the shape, this shape here is, this is from here to here. This guy is 109.5. So if we had carbon, okay, carbon has 4 attachments. Each one of these is going to be 109.5 degrees from each other. Okay, so it's considered to be tetrahedral because there's 4 attachments and the shape that it makes. It makes a tetrahedral shape. Okay, are you with me there?
Mm-hmm.
Okay, so we have boron. Boron has 3 valence electrons. Now, boron is kind of weird. It doesn't really like to have 8 around it. Don't know why. Can't explain it. So it prefers only to have 6 around it. So what it will do is it'll make 3 bonds, attachments. So now we have 3 attachments. So these guys can be in a single plane, right? Plane meaning like a sheet, same area. You know, where this one guy, when it was 4 attachments, we had one that was kind of sticking out in front like this. And the way it is that the electrons want to be as far away, or the electron pairs or the attachments or the atoms, they want to be as far away from each other as they can possibly be, right? Because that gives them room to sit there and do their job. They can move and stuff like that. They don't want to be constrained, right? So they want as much room as they can possibly get. But have you ever seen like a person on a dance floor that really is like really dancing? I mean, they're just trying to take up as much room and they're just like going all crazy, right? And everybody around them give them as much room as they want to because they know if they get too close to that person, they're gonna get hit or something, right? You seen that person on the dance floor?
Yeah, that was back in the days when they had dance battles.
Exactly, yeah. Yeah, so everybody gives them enough room, right? So that's what the electrons are doing to each other. They're giving themselves enough room so that they can do what they need to do, right? So in the case of 3 attachments, 1, 2, 3, its EPG would be 3. Its geometry would be trigonal planar because 1, 2, 3, tri meaning 3, gonal, you know, like a trigon, 3 parts, planar, same plane. Now, if we only have 2 attachments, these guys are going to try again, be as far away they can be from each other. So in this case, the angle here was going to be, let me put this in a different color. The angle in purple. So this guy's going to be 120, 120, and 120 because we know a circle is 360. This guy here, each of these angles are going to be 109.5. So if we had it in all those different planes, it'll all be 109.5. Okay. So if it's 2 attachments, so that's 4 attachments here, 3 attachments, trigonal planar, and then 2 attachments, this guy is going to be linear. So EPG to linear. And you guys know what linear is, a line, right? Doesn't that look like a line?
Yep.
Okay. Okay, so 2 attachments, linear, 3 attachments, trigonal planar, 4 attachments, okay? And that's for the electron pair geometry. Let me type that out for you. Okay. Now, the electron pair geometry only talks, it looks at both the electron pairs. So like this guy has an electron pair geometry, has 4 attachments, 1, 2, 3, and then that electron pair would count as math. So it's EPG, it's electron pair geometry, is going to be 4 attachments is what again?
Tetrahedral.
Tetrahedral. And my spelling is horrible. Let's see, tetrahedral. Okay, so this guy, its electron pair geometry is tetrahedral. Now, when we talk about the molecular geometry, that's going to be a little bit different. The molecular geometry is, in this case, so we take a tetrahedral. So we're just saying that this is a lone pair up here, right? But that lone pair is going to act as if it isn't there at all. And so then, so it's not going to be visible. So for the molecular geometry, you're not going to see the lone pair, but the lone pair is going to have its effect. It's going to make that tetrahedral shape to it, right? And in this case, if you look at it, here's the center atom, here are the attachments, right? Does that look like a pyramid? If it had a bottom, wouldn't it look like a pyramid?
Yeah.
Okay, so this guy is called trigonal pyramidal. And that would be its molecular geometry. Okay. Are you guys with me so far? Okay. So when we have water, H2O, we know that its fluid dot structure looks like this. So if we went with its EPG, how many attachments does it have?
Two lone pairs.
It has 2 lone pairs and it also has 2, so you want to count them all. So that's 2 lone pairs, that's 2 plus the 2 hydrogens, right? So that's a total of 4 attachments. So then what would be its electron pair geometry? It's EPG.
The Tetrahedral.
Tetrahedral, that's right.
Yeah.
Tetrahedral. Tetrahedral.
Tetrahedral. Sorry.
That's right. Yeah, that's all right. It's a learning process. If I can learn how to spell it, then I'm sure you can learn how to say it. Still working on it. Okay, so tetrahedral. Okay, so it's tetrahedral. Now, the molecular geometry is the way it's going to behave. Your two lone pairs are going to sit up here, and it's going to push down on those two hydrogens. So literally, those hydrogens are going to look like this, and then my hand represents that oxygen. These represents each of the hydrogens. So that structure is going to be what we call bent or angular. Okay, does that make sense?
Dr. Henry, I'm going to log back. I'm going to log out and log in on my phone just to see if I'm doing this right.
Okay, sounds good.
So Dr. Henry, can you see my screen, my
Yep.
Zoom?
Yep.
So like that is what you want us to do basically?
Yep. That
Because
is
you're just
exactly-
wanting us to basically show the angles for everything, right?
Yeah, it's partially showing the angles and then also showing, the octet, make sure things are obeying the octet rule.
Okay.
We're gonna have what we call exceptions here soon. So
Wait, so is bent or angular part of the EPG? Or is
no,
it just
that is part of the molecular geometry.
okay.
Good question.
So one of them is just chlorine, right? What do you want us to do for that one?
So what are you gonna do for that?
Oh, it's just just chlorine.
It's
A
just
negative
chlorine.
charge. Chlorine.
Yep.
Okay. So do you just want us to show you these in the Zoom, or you want us to take pictures of them for the lab?
Since you already did it, you could actually you could just show it to me in the Zoom. That'll be fine.
Okay. So because I already did.
Yeah, if you wanted to take pictures, you could take pictures as well and put them in your lab.
So this should be the. So this is it. Can you see my screen now?
Yep.
So that's good.
It depends.
Okay.
Okay. Looks good.
Okay. So then I already showed you the H2O.
Yep.
Or this isn't the H2O. This is H2O over here. What am I looking at? Getting myself confused.
So that's your N2, 2 plus?
Yeah.
Or 1 plus, 1 plus, right?
Yeah, I believe so.
Yeah.
It doesn't show, so it'd just be 1.
Or not 1 plus, 1 minus. It'll be NO2 minus. Okay, so we have, make a little quick table.
Dr. Henry, I have a conceptual question that I tried looking up to better understand this, but electrons orbit atoms because of protons, right? They're attracted to the protons.
That's right, it keeps them in orbit, yes.
So do the number of protons ever affect the behavior of the electrons?
Yes, it does, because in the case of the more protons that you have, it's going to either pull the electrons in closer, or if you have more electrons, it's going to be a little bit further out. Does that make sense?
Yeah, I can understand that. So does that mean that whenever an electron leaves an atom, there is some kind of force of energy also like pulled on the atom as the electron leaves?
Yes, that does. So if an electron does leave the atom, it does have an effect. And so that's why it typically takes a certain amount of energy to help remove that electron. So when we were talking about the ionization energy, right?
Mhm.
There is an amount of energy that has to be added before that electron is able.
Is able to leave. Okay.
Good question.
Does this have to do with why boron has such a strange like number of electrons around it, or does that have nothing to do with that?
It does actually. It does. Kind of where it's located. It's where it's located at the number of protons it has, and then there is also beryllium. Beryllium is actually, it's a metal. It's considered to be a metal, but it doesn't behave like a metal. It likes to be, it likes to form covalent bonds, but it only likes to have 4 things around it. And so it's one of those ones that are
Oh,
just
that's
kind of-
strange.
exactly. It's an oddball.
Hmm. Okay, I tried looking stuff on Google for this stuff, and nothing ever came back that explained it to me. So thank you. I just wanted to know.
Wait, so real quick, with the ones that we have, we're supposed to assemble. I'm just kind of confused on.
So you want to put the compound together. So you got to make sure that you have the center atom, the right center atom, and you want to make sure that you have the right number of attachments around them.
Okay.
Okay, so like, it's really the one that you're going to have to do this with is the second, number 2. Number 3 is a lot more, but it's just actually just drawing it. And if you use the tile, you can use the tiles, but you're not required to use the tiles.
Okay. And it doesn't matter because mine's different from like the one that it's showing at the top on like canvas is oxygen and sulfur. And then I have nitrogen and chlorine.
What do you mean by one that's showing?
Like there's a thing where it show like you can print out and like the
Oh, yeah.
square.
Yeah. Okay. Yeah. You guys have a different set of tiles than, but you should be able to do all the ones that were here.
On 2. Okay.
On 2. That is correct. And so that's the one that I want you to do your tiles with. This one, you don't have to do your tiles. You're just going to draw them. So the tiles are kind of like a crutch to build you up to that Lewis dot structure independently.
Okay, so like H.
Dr. Henry, how do you want us to draw them? Like, where do you want us to put them?
In a notebook, and then you're going to upload your notebook. Or if you guys
Just take a picture of it.
Yep. And then upload it. Yep. That'll be the easiest way.
So is the whole lab going to be in a sheets?
Yep.
Just document like last time?
Yep.
And just put all the numbers in basically, and then upload the pictures?
That's correct.
Okay.
When is this lab due, Dr. Henry?
It's due Friday.
Oh, okay. And already?
Yeah, you've had it for 2 weeks now.
And it's called having a jump start then.
You're technically behind on a jump start.
I should have done that.
I was kind of confused, like on number 2, the first one, like H2O. How do I build it with nitrogen and chlorine? Like those are my main.
No, but you have more than nitrogen and chlorine. You should have all of them. You should have nitrogen. You should have 4. You guys came with 4 sheets. If you're at Harnell, or you're not at Harnell, you're here.
Yeah.
Yeah, you should have a total of 5 sheets. 5 sheets. So you should have one that's chlorine.
Check
And
your
then
lab
carbon?
bag. In mine, the sheets were like mixed up with the other paperwork.
That might be why.
It might be hidden in part of it. I thought I didn't have enough either. So just double check.
Oh. Okay, all right. No, we're good now. No, I was sitting here and all I literally had was one sheet, and then it was like all nitrogen, chlorine, and I'm just looking at those like, well, what am I supposed to do? Okay. Gosh dang it, I gotta cut these out. Okay.
You guys are not like really good kids, were you? You don't open up your bag and take everything, and when you get it, first thing I always do, anything I get, I rip open the bag and put it all on the floor.
Yeah, I don't know how I didn't see the rest of the sheet. That's why I was sitting here like wondering like how am I supposed to put this with different? I don't even have all the. I see it now. All right, well, just give me a minute here to try and speed cut these real quick.
See, I see somebody's chatting. Hold on. Do you see him, Aaron?
I'm looking at the lab, and the only sheet that's attached to the lab is the ones with oxygen and sulfur on them.
It doesn't have them all.
No, it doesn't have them all. I'm missing the sheet with the hydrogen.
Okay, and you checked your bag?
Yeah, I'm pretty sure I cut them out and lost a few.
Okay. Let's see. Huh. That is really weird. Hold on. It also could be just showing you the one page. Nope, I guess not. Okay, so let me attach. Let's see why I did not attach them all. Okay, Aaron, you should be able to get it now.
All right, thank you.
No problem.
Dr. Henry, can I show you what I'm doing through my phone just to make sure if I'm having an idea what I'm doing?
Sure. Yes. Can you hear me?
I heard you.
Dr. Henry, I have another really weird off-topic question.
Yep.
So if electrons are particles, do they have a wave counterpart, or are they always just particles?
They're both. They're
They're both a wave and a particle.
yes. So
And-
that's one of the things. They kind of have this duality to it.
And the energy, so can electrons move position from the energy of like a photon striking them? Or-
Yes.
Okay.
Yes.
So could you like this might be impossible to experiment or to test, but just theoretically to understand it, could you then, like, let's say you had a perfect miniature laser, could you replicate, so like say an atom doesn't have an electron and you want to like simulate an electron with light, could you do that? Because I know like the light wave, all that stuff, if it's the same energy, would it change the property of the atom as a whole, or is that not possible? Is the electron itself like inherently negative or fundamental?
I'm not sure what you're asking.
So like, because I know that when an atom has like a different number of electrons, it kind of changes its like properties and stuff.
Yep.
Could you artificially generate this change with just like some, like if you can manipulate photons in such a way, you could just change the whole property by, even though the electron's not there, you can artificially create like an electron effect with focused photons in some way, or is that not possible?
I have to give that some thought. So you're just basically saying that we're just going to use photons, and the fact that there's no surface or anything in the way, so you're just going to basically hit a photon hitting another photon, or are you just gotta?
I think that would be the idea, that you'd have to have like photons striking each other to like create the simulation that it might be like an electron there or something.
Yeah.
But is it that the electron itself is like inherently negative, so it has a special property with a proton, or can light simulate that or not in any way?
Okay, so light. I think I understand what you're saying, right? So you're right. So electrons are negative, right? So, but the photon hitting the electron is actually gonna cause, it's basically causing the electron to get excited in a sense, right? So then all that energy from that photon is being stored up in the electron. And then when that electron drops back down, it goes back down. So what you're trying to say is, so if I don't have the electron there, could I simulate that effect?
Right.
So, and in a sense, you're saying that if I have a photon striking another photon, is there going to be an effect on that photon?
Yeah, on the atom itself.
Well, but So you're saying that if the photon is exciting, not necessarily the electron, but it's actually hitting like a proton. It's like we removed all the electrons. So if we have the H plus, and that's just a proton. Right.
My question might be like inherently stupid, so it might just be nonsensical. But so like maybe I'm understanding this incorrectly, which is why I asked the question. But if the electron itself, is affected by energy, like a photon,
That's
then could a photon together, like if you could manipulate a photon in such a way, could you use a photon like an electron and fundamentally change the properties of an atom, even though there is an electron there? Or are those changes fundamental to the electron charge and the electron being there?
So it's fundamental to the electron, because the electron is what's going to be, it's going to gain that energy. However, so if we think about like a neutron and a proton, right? So if we strike a neutron or a proton with, let's say, energy, there is an effect, but you got to get to that neutron and that proton to get there. And usually you have the electrons that are shielding it, and those electrons are what are going to absorb some of that energy.
Oh, I see. So the energy itself isn't changing the electron, it's just changing its place around the atom.
That's right.
Oh, okay. Yeah. Okay. Now, okay. I understand now why my question makes no sense whatsoever. I didn't understand like what I guess what I'm saying is, what makes an electron inherently different and more fundamental than like can an electron itself decay? Can it break down to something simpler, or is it just an electron?
Electron decay. So no, electrons typically don't decay. Neutrons, but not electrons. And so I'm trying to think of a situation where we'll have because electron, again, it's that fundamental. You excite it, it comes back down. You excite it, it comes back down. It's pretty simple. But neutrons, on the other hand, can decay. And that's how we end up with our stable isotope.
I see.
So, but I gotta actually have to think about that too, because it's actually the nucleus that's decaying. So you're losing the neutrons. So it's not like the neutrons are gone. They're just being, I guess, removed or transferred, or So, it's still that sense of, and that's the thing about nuclear, when you talk about nuclear, because that starts messing around with the concept of law of conservation, right?
Oh, it starts breaking down, like,
Yeah.
because you break down the actual matter into pure energy.
Yes, in that sense, right?
Okay. I think I'm confusing myself, but I think I understand. So a neutron itself is also fundamental. They can't break down any further.
Yeah, a neutron. Well, okay, so you have to talk to the physicists. They'll know more about this part. So there's beliefs that there are particles that are smaller than our subatomic, proton, neutron, electron. Okay, and so since there are thought to be things that are even smaller than those, and the problem is, it's all theoretical right now. There hasn't been anything to kind of sustain the validity of it.
So wait, can electrons break down further, or are they?
In theory, right? According to a physicist or a couple of physicists, theoretical physicists, they can, right? And but again, that's according to, but nobody's been able to see that. In the case of neutrons, we see the decay, right? And so as a result of that decay, there's a suggestion that there are smaller particles. Things are being broken down into smaller particles. What is it? I can't even think of the terms that they use right now. It'll come to me later today. It'll come to me, or tonight when I'm sleeping. But I'll get to you the name of the particles that they make reference to. But so there's a belief that at least the neutron and potentially the proton can, for sure.
So what makes an electron like inherently different from a proton? or like from the other ones? If they're all like made up of these things that decay.
Yeah, but they're not necessarily made up of the same thing. Okay, like a proton
Oh,
and
okay.
an electron are two different, right?
Mhm.
That's kind of like, even though like male and female, we come from the same development,
Right.
but there are distinctions between us, right?
Mhm.
So
So wait, what are photons then? I don't understand.
photons they're like bundles. They're just bundles of energy, right?
Mhm.
So it's just energy that is it's just energy, right?
Mhm.
Light energy, essentially.
And can those break down further, or those are just like particles, energy? Like they're
Well,
only particles.
It's not necessarily because, okay, you got to think about it. A single photon, right? So I was talking to like students about energy, right? So we think about energy in terms of packet. So a photon is like a bundle of energy, right? And so in theory, it's a packet of energy. And so you can actually break that down to smaller packets. Kind of like, you get a big old thing of
Oh,
sugar,
I see. Yeah. Mhm. I see. So a photon itself is just like matter totally broken down, and you can just have more of that energy from the broken down matter.
That's right. Or
Okay.
it's, well, not necessarily matter that is broken down because it's not quite matter. It's energy, right? Photon is considered to be energy,
Mhm.
right? And
Oh,
so it's
man.
not quite matter. It pertains to matter, but
Mhm.
it's not quite matter, So like energy is like kinetic energy is a result of matter, but it's not necessarily just matter.
Oh, I see.
Yeah.
Right. Yeah, and it's not photons either. It's the like. Okay, I see. Man, I'm gonna think about this more. So, okay, so all I really need to know is that electrons are fundamentally negative and protons are fundamentally positive, and these affect each other because of that. And the neutrons are just a part of protons and they're neutral in that way to make up the nucleus. Okay.
And some way they help stabilize that nucleus. And so like when we start talking about those elements that are higher, 118, 119, so they need the right amount of neutrons to keep them stable, keep them in existence. Otherwise, it kind of falls apart. Does that make sense?
Yeah. Right. Because the protons and neutrons make up the nucleus and they have like a bond together, and if that bond's uneven, the nucleus will rip apart. Is that what you're saying?
Yeah, but it's not quite so protons and neutrons, but it's not quite a 1-to-1 ratio, right? So there's never a 1-to-1 ratio. There's just so many there that help stabilize it, So it's kind of like, I don't know how it's working, but it's kind of like, how you're packing up a vase or something like that, and you're not packing 1-to-1 cushion to the vase. You're just putting a whole bunch in there so it doesn't move around and it doesn't, do anything crazy, right? You kind of keep it positioned. So I think the neutrons are kind of acting like that. So they're kind of like that cushion that we put like a glass vase in when we're trying to send it across.
Okay. So this makes me think then that like maybe I'm totally wrong. I'm sorry if I'm getting off topic for anyone else wants to ask questions. I'm just working on this and I had some questions. But does that mean that technically any element can be broken down for energy like uranium? Or
yeah, technically anyone can, but uranium is ideal because it provides enough energy that it doesn't it's not going to destroy a whole world, in a sense. And so you want something that can give you enough energy to do what you want to do, and it doesn't take a lot of energy to do that.
I see. Oh, it's just more efficient.
Exactly.
Okay,
so it's that trade-off. So yeah, so in theory, all of them could go through that process, but there are ones that are going to be better than others. And uranium happens to be one of the better ones.
Wouldn't that mean that the ones that are even higher would be better, or do they just not last quite as long?
It's the time that they last, and then also how much energy you can actually get out of them. Because you also have to take into consideration the effects that that utilizing them in that sense, what is that going to have? What are you going to get out of it, right?
Mhm.
And so what are your waste products in a sense? And so you're going to have to take that into consideration as well, as much as just the energy, the pure energy itself.
Mhm. I see. I see.
Does that make sense?
Yeah, it does, but it also makes me think that maybe like there would be some more experiments more valuable to study from if they're not going to be like uranium, which is a lot of excess energy. But it might just be that they're all the same, so it doesn't really matter. But like, has anyone ever tried to do this with like copper or iron to see the effects, what happens, or is it just all like the same things, don't need to?
You know, I can't say for sure, but I'm pretty sure that somebody has tried other,
Mhm.
and then they were trying to look at the outcomes from it.
Mhm.
And they usually, like anything that's been done, or in that regard, done for one atom has been done for others. And they
Mhm.
probably measured the amount of energy that you're getting. Either it wasn't enough to be worthwhile,
Mhm.
or it was too much that caused too much damage and wouldn't be controllable,
Mhm.
you know, on a mass scale. And so,
I see.
yeah, so there's a lot of factors when you're thinking about in terms of energy production. There's a lot of factors that you want to take into consideration.
Mhm.
And then also you have to take into consideration that a lot of times when it's done, it was done at a time period that we're still kind of young in terms of technology and things that we're capable of, or what we believe we're capable of. And so some of it may need to be revisited. So
Oh man.
does that make sense?
Yeah, no, it makes sense. I'm just like exploring it mentally and thinking about how it affects the other things. All right, that's all the questions I have. I'm sorry for
Yeah, that's all right. No, I like when you guys have questions like that, because it makes me think, it gives me a little excitement as well too.
Real quick, Dr. Henry, I have
Yep.
a question because I missed it because I was cutting everything out. But what did you say were, I know you said the white ones were the valence electrons, right? What are the black ones?
No. The black ones
Or
are
which
supposed
would,
to the black ones are supposed to be the valence electrons,
oh, okay, the black ones.
and the white ones are supposed to be the open space. There are a couple of them that kind of screwed up.
Okay, the open space. Okay.
Yeah. So like for instance, hydrogen is missing its black electron.
Ah, okay.
Yeah.
Got it. So would it be like easier if I like hole punch them so I know it's an open space?
Yeah, that would be easier. Yeah,
Awesome. Okay. Okay.
it's actually a good idea.
Hey, Dr. Henry.
Yep.
Can I show you my other ones that I did?
Let me stop sharing my screen.
Just AirPods just died. Can you still hear me?
I can still hear you.
All right. So can you see it on my screen?
Okay. So you're saying, and this is with the additional electron?
On the thing, it just shows, where was it? The NO2.
NO2, no negative or anything like that?
No, there's nothing on it.
Okay. So in that case, are we going to obey the octet rule? I'm curious.
Yeah, we would have to, right?
But can we? How many valence electrons does nitrogen have?
Nitrogen, for the total, where did I put it? I wrote it down. Hold on. The whole thing should have 17, I believe, right?
Nitrogen? Oh, you're saying altogether 7. Okay, so you're right. So 6. So nitrogen has 5 valence electrons. So that's an odd number. So can you show me? I mean, I have $100 somewhere. Probably don't have access to it right now, but hopefully next week I'll have it. But I have $100 saying that you cannot obey the octet rule with 17 electrons. Are you willing to make that bet?
I would not want to bet against you.
Good, I like that. That makes me feel good. So, because it's an odd number, there's no way that you can ever obey the octet rule in that number, right? It's an odd number. You can turn it any way you want to. You're always going to end up with an odd number. So one of them is always going to be less than the other. So you can't really show the way it should look because, you know, you don't have that odd number. Well, it's kind of set up to work out perfectly, right? But if you look at it, actually, no, it does. It works out perfectly. Because if you look at it, right? So you're saying these guys are sharing, so they're sharing one bond between the hydrogen and the oxygen. So they're sharing one bond there because you have two black there, and then you have two black here. So you're sharing one bond there, one bond here. And then you have one lone pair, and then you have a lone pair that doesn't have an electron, right? So then that means that you have around nitrogen I'm trying to write on your thing, but you have 2 electrons being shared between the oxygen and nitrogen, so that's 2. The other oxygen and nitrogen, so that's 4. There's the lone pair up top, so that's 6. And then there's the one at the very, very top. That's 7. So nitrogen, because it's weaker than oxygen, it's going to end up with 7 electrons around it instead of 8. So it actually disobeys the octet rule because it has an odd number of electrons overall. So you have 17 electrons instead of having 18. Does that make sense?
Yeah. So then
So-
that would
so
be as good
it's
as I can do
perfect,
it with
right?
these. Right?
What was that?
Right.
Yeah.
I said,
So
so that's as
you're-
good as I can do it with this model.
Yeah. Well, no, you did it perfectly. That's the way it was supposed to be. It looks. So your model is right. I'm not saying your model is wrong, but I wanted you to be aware that it does not obey the octet.
Okay. Gotcha. Thanks.
No problem.
All right, Dr. Henry, I think I got this down. I'll probably finish it up on my own.
Okay.
Right.
Sounds good. I will
Good
see you
to-
guys. Yeah. For anybody who's heading out, I'll see you guys on Thursday.
Right.
How's everyone else doing? Good, bad, ugly?
I'm almost done here. I wanted to ask, so for the last 8, I believe it's 8 here, I want to ask for Lewis dot structure. Do you want us just to draw it out or do you want us to use the things for even those as well?
Draw them out.
Okay.
Yeah.
All right.
Yeah.
Okay,
the
I'm
tiles
ahead
are
out
just
here.
to kind of to get you guys started. And then-
Okay. All right, I'm gonna head out here. Have a good one, everybody.
Okay. See ya.
Dr. Henry?
Yep.
Oh, and you know how I told you I was going to show you what I have so far, but I'm pretty sure I'm really incorrect, but this is what I have an idea so far.
Okay. Let's see.
So right now, before I show it to you, you said we're just doing number 2, correct?
Yeah. Number 2 is the one you're doing with the tiles.
Okay. What's the difference between number 1 and number 2? Because it's similar to that, but it's just one element, you know?
Yeah. So can you make a compound with one element?
No,
You just have one element. Yeah. So it's just an element, right?
right.
And so when we're talking about showing you where things are being shared, and you're showing me the structure, and it's the center atom, then you need more than one element, right?
Right. All this, are we doing this like in a Google document or on Google Sheets?
You can do it in a Google document, or you can do it on Google Sheets. It's up to you.
Oh, okay, so it doesn't matter to them?
No, doesn't matter. As long as you answer all the questions.
Okay. And the last 2, oh, it's a lot of drawings. For that, can we do them on a scratch paper and then take a picture of it and then put the picture into that in a document?
Okay. repeat that, please, one more time.
Okay, let me show it.
Okay.
Can we take like do this on scratch paper
Yes.
and then take a picture of it?
Yes. Yes, you can.
Okay. Everything seems like a piece of cake, but why does something have to interfere? Like I can't do it.
What do you mean by you can't do it?
Well, I'm not sure if I'm quite right with this. This is what I have so far, but it's an idea. But
Okay, let's see.
they're not officially taped yet, though. That's the good news.
Okay.
So this is what I have for SO4, and then with the -2.
Okay. So are you lining them up so that the ones that have empties?
What was that?
Okay. So you said SO4 -2?
Right. This is what I have
Okay.
so far, and what I have so far. But you can say I'm wrong because I'm pretty sure I am wrong.
Okay. So, oh yeah, I kind of set you guys up a little bit. So you guys are missing, so that oxygen there, right?
Yeah.
Let's see. Do I have?
What confuses me with that one is that there's 4 oxygens, but there's like it's taking away or gaining an electron actually.
Is it gaining 1 electron or is it gaining 2 electrons?
2.
Okay. So then in that case, it's gaining an additional electron. So you're right, you have one that has an additional one.
Right.
And then we actually technically need another oxygen that is negative. I could add another one for you.
Oh.
Or we could add a sulfur that would have the electron around it, one or the other. You understand?
Okay.
Yeah.
Right. So it has to be one of these 2, right?
Well, those both have 6 around them, but one is set up for another structure.
Right.
And so I'll have to fix it's my fault. It's because I didn't have another negative oxygen or a negative sulfur so that it had an electron on it. And so you have one that has a plus. Yeah.
So this one is right? Or no?
The structure is it's almost right. But the way you would do it is that, remember, they're sharing electrons.
Right.
Where are they sharing electrons at?
Where are they sharing the electrons at?
So look, okay, remember the dots represent the number of valence electrons, right?
Right.
Okay.
Yes.
The black dots, the white dots are open spaces.
Right.
Where you can put electrons.
Yes.
Okay. Now, if you know that, that's also messed up too, that's missing. I have to fix that one as well. Okay. You guys are helping me catch all my mistakes.
Dr. Henry, I have a question.
Yeah.
So you said that the white ones are open space or the
Yes.
black ones?
Yes, the white ones are open space and the black ones are supposed to be dots, right?
Okay.
So, but hydrogen is a little messed up. It should have 2. It should have one that's an open space and one that's a dot.
Oh, so hydrogen should have been a black dot then.
Yeah, it should have 1 black dot and 1 white dot. Yes.
I see.
Yeah. So I'm gonna have to do some fixing here.
And what about for the first one, Dr. Henry? This is similar.
Okay, so yeah, so that one is good. Only thing where your hydrogens are going to be located at,
right?
So you want to put the dot as if So if let me see if I. Okay, so if you slide it underneath, right?
Right.
Where it says oxygen at, slide your hydrogen under there where it says oxygen.
This one?
Yes. No. The other way. More closer, directly where the black dot is at. Do you see where the black dot's at?
Yeah.
Okay.
Right there?
Not there. At the bottom. It says oxygen, and then underneath you have a white dot and a black dot.
Okay, tell me where to shift.
Down.
Down?
Now go to your right. Okay, right there. Right, stop right there. Okay, so hydrogen is going to be providing a black dot, and oxygen is going to be providing a black dot. So that would be a bond shared between them. Okay?
Right.
And then, so that's the same thing with the hydrogen on the side. So if you turn it, rotate your hydrogen. Right there.
Okay.
No, not that far, back the other way. Okay, so pretend that white dot is really a black.
Right.
Okay, so it will be connecting to that other oxygen where that white dot is at.
Oh, okay.
So the white dot represents an open spot that you can put an electron. For sure.
Okay.
Okay, does that make
So-
sense?
Yeah, so it'll be placed like this in total.
That's right.
Okay.
So since the hydrogens don't have the black dot, can we
You can
like
draw it in.
one or not?
Yeah,
Are they all going to be in the same spot, like right
Yeah.
next to it?
yeah, it doesn't matter, just next to it anywhere. Yeah, perfect.
Okay.
Good job.
So Dr. Henry, I'm not sure if I got this one right or not, but I'm not sure if it's because of the little cards we have or whether I'm just not doing it right, or if maybe I did. I'm not sure.
Okay.
Can you see it?
Yep, I see it. Okay, so let's.
Because I was trying to do like a bond down here, but I don't know what to do with these because I feel like they're not lining up the way they're supposed to.
Okay. Okay, so I'll say the same thing that I said to Alan. So what you want to do is you want to set it up so that your electrons, the open spots are going to be taking electrons. So the white spots are technically taking electrons, and the black spots are the electrons that are going to be given.
So I would move like this oxygen over here is what you're saying?
I would move the oxygen that has, okay, so there's a couple of oxygen. Right? So you have one that has two empty spots, or you have two of them that have two empty spots, like this.
Right.
Like that one. You have two of them that are like that, right? That have
With the
two
double
white
empty.
spots. Yeah. Okay, so I would use those guys, right? And then I would take that to the one that has two black spots, nitrogen, because that's
Okay, I
where
got you.
it would go.
So
So,
So
yeah,
the
you're
two
gonna have
black,
to
the two
respect-
black.
yeah,
So and then I can move like this one here to this part here,
that's right. Yeah.
and then it would be right.
Yeah.
Okay, gotcha. All right, I'll do that real quick.
Dr. Henry, you want these in pictures as well?
If you just show me in the Zoom meeting, you don't have to worry about the pictures. Just say in Zoom meeting.
Okay.
Okay, Dr. Henry, so it'd be like this. If you can see my screen, I'm not sure.
Let's see. Let's see.
Or would I want to change this
4, 6.
oxygen to one like this one?
Okay, hold on. Let's do the count here, right? We got 2, 4, 6, 8. You have 10 around nitrogen, the way that you have it set up. Do you understand? So the blacks represent the electrons that are going to be, the black dots represent electrons that you're going to be using for bonding, right? So the oxygen that's on the left-hand side, that's 2, 4, right?
So I wouldn't want to put 2 on this nitrogen is what you're saying. I just want to put 1.
That's exactly. So it's going to be, you're going to be using the open spot, the white dots on like the oxygen,
Wait, so you
attaching it to the dark spot
put it like this, you mean?
like that. Yes, because then that's 2,
Okay.
4, 6.
Okay.
You're moving too fast for me. There. So that's 2,
Sorry.
4, 6, 8 around that nitrogen. And then you have 2, 4, 6, 8 around that oxygen. And then you have 2, 4, 6, 8 around the oxygen down there. and then you have 2, 4, 6, 8 around that oxygen, and then you have 2 for hydrogen. So that's perfect.
Dr. I don't know. This is for number. This is the number 2.
Let me see.
Number.
Okay, so I see 2 of you, Tucker, so I'm confused. Which of us am I looking at?
Hey, I'm trying to switch it around.
Can you see it?
Let's see.
I think I have my laptop's on there too.
Laptop's on there too.
Okay, there we go. Yeah. Okay, so let's look at your structure there, Tucker. Right. So if the black dots represents the valence electrons and electrons that are being shared, do me a favor, count all the electrons around the sulfur.
Around the
sulfur.
So 6, right? Or no, because you got to count the double. 4. It'd be 12. If you like counted the double, because don't you go 2, 4?
So count each of the dots that are be around the sulfur.
Just in sulfur?
Just around sulfur right now. Then we'll get to the oxygen.
Okay, 6.
Okay. So no, I mean, even the ones that are being shared that are on both parts. So you have how many dots total? Black dots.
That are being shared even with
Here, I'm going to put you in the middle so we can pin you. Highlighting your. Okay, so you just stopped. Hold on. And I'm having trouble. Are you there? Did I lose you?
2, 4.
Yeah, I'm here.
Okay. Let's see. I don't see your image anymore. There we go. Okay. So now you see your image there, right? So count the dots, the black dots that are around the sulfur, even if they're on the oxygen card. Count them. That would be around the sulfur.
Uh, 12?
12.
Or no?
Keep counting. Come on, you could do better. Black dots.
14.
Yeah, 14. Okay.
Okay, yeah, I was missing out on the list.
Is that more than 8?
Yes, very much.
Okay, so the goal is you want to have it set up so that you have 8 around them all. And so you may have to find the right oxygen molecules, right? So that they'll set up the other way. Now remember, the white dots mean that they're open spaces. There's no electrons there, right? The black dots mean that those are valence electrons.
Okay.
Okay, so you want to try to set it up so that there's 8 around everybody.
Okay.
Dr. Henry, are you still with him or?
No, I'm listening to you. I'm listening to all of you guys.
Oh, okay. Then. So I already got number 1 down. What about if for chlorine? It says right here you have 1 chlorine, but with 1 negative charge, and I have all my 4 chlorines here.
Let's see. So if you have 1 chlorine, right?
Right.
So then it's just chlorine. So you don't have to worry about that one really. You just have to take a picture of the chlorine, but it technically has a negative charge. So that means that you're adding an additional electron. You're adding a dot.
Okay, so it would just be this one by itself then.
Yep.
Okay, that one's down then. All right, number 1 check, number 4 check. For number 3, when you have NO2, which is nitrate or nitrite, I think. One of those two.
Okay.
I believe that I got these.
Okay. So let's see. So that's my messed up nitrogen. Technically, there should be 5 black dots there.
Oh, okay.
There for the nitrogen. So you want to orient it so that it
This
all
one?
fits. That one will work. That one would work. Yeah, that one actually would work well. And
All
then
right, I
you want to
replaced
use and then you want to use the oxygen where you have, well, it'll sort of work. There's another one that would probably work better.
These are
Yeah.
my oxygens that are remaining.
Okay. Well, you can recycle, just take a picture with it and you're good to go. So let's see.
Yeah.
Hold on. Yeah, so you have the one that has 2, the 2 spotter.
Right.
Yeah, so you could use that one on the other side.
This one?
Yeah.
So like this?
Yep.
So this is how it ended up overall.
Let's see. 1, 2, 3. So count the number of electrons around both of them and see if it
In
works
total?
out. Yep. Well, no, around each one independently, each one.
Okay. Even the white dots, right?
Yeah.
On all of these, right?
Yep. Well,
Okay.
not the white ones. Don't count the white ones because the white ones are open. Remember,
Okay.
only the black ones.
They have 6 oxygens on both of them. So that would be 12. And for nitrogen, there would be 5 with 3 open spots. Dr. Henry?
I'm here. I'm listening.
Oh, for oxygens, I got for both oxygens, there's 6 of them. So that would be a total of 12.
Okay, so around the nitrogen.
Around the nitrogen.
Around the nitrogen. So is that too many?
Yes.
Okay, so you want to set it up so that you end up with just 8 around the nitrogen, or in this case, it can only have, it's a special case, it only can have 7 around it.
Oh, okay.
Okay, because nitrogen has 5 valence electrons, oxygen has 6, right? And so that's
Right.
12 plus 5, that's 17,
Right.
right? So
would
that
I
makes-
replace it with one of these oxygens?
did you replace it with one of these? Yeah, you can use one of those oxygens. I would so use the one, okay, you see the one that has the double spot?
This
That
one?
one. Grab that one.
All right.
Okay. And then use a different nitrogen too. So use the nitrogen. There should be one that has a 2 and a 1. It has 2, 2, 1. Yeah,
Mm.
that.
This one?
Nope. That, yeah. Wait. That's 1, 2, 3. Not that one. That one has too many. Man, I have too many screw ups. So there should be one. So that's the negative one.
Oh, there's one right here. That was the one I was going to use.
Yep, that one right there.
Okay. And so this is what I have now. I was going to use that for
Okay.
NH3.
Yeah. So then that
No.
one right there, right? So this is a perfect one, right?
All
So
right.
you see where you have 2 dots for nitrogen?
Yes. Right.
So connect that oxygen right there. Okay.
All right.
And then you see the other oxygen. You're going to connect
Right.
it where it has 2 dots, 2 black dots. No, the other, yeah, well, that won't work because then you won't have 8 around oxygen, will you?
Right.
Okay.
So
if you do
right
it the other way, and
on the
flip
top.
it so that the white, is matched up with the black. There you go. No, the white is, there you go. Okay.
Okay. So that's for NO2, right?
Okay, so well, first we want to make sure that that's right, because we also need to make sure that we get enough around nitrogen, right?
Right.
So if I flip it, let's flip the one on the right-hand side.
This one?
Yep. So that you have one black. So you have both blacks showing. So flip it, turn it, rotate it. No, not flip it. No, rotate it. There we go, right there. Right there. And then so that both blacks are showing. There we go. Okay, so that's the way it's, now count the number of electrons around the oxygen.
In total, right?
In total around the oxygen.
There's 6 right here.
And then there's the 2 that it's sharing, right?
8.
With
Yeah.
the nitrogen, 8. Okay, so that's 8 around that oxygen. Now look at the
Right.
other oxygen. How many is around that one?
8 as well.
Okay. And then how many is around the nitrogen?
There are 8.
Is it 8? Are you sure?
There's 5.
So there's 5, but remember, count the ones that they're sharing too. Only the black dots. Only the black dots.
There's only 5 on.
There's 5 on the nitrogen, but then how many is it sharing with the oxygen?
How many?
Yeah, what is it sharing? Look on the right-hand side. How many oxygens are facing? Do me a favor. Connect the oxygen and where you had it connected before. Put it closer. No, don't turn it the way that you had it just now. Just push it closer. Push it closer. Because that represents not underneath it, because they're 2, remember, 2 black dots, right? So each of them are electrons. The white dots are nothing there, okay? So you're saying that they're sharing how many electrons there between that oxygen and that nitrogen? How many electrons are between the 2?
4.
4, okay, so that's 4. Now count the electrons that are being shared between the other oxygen and the nitrogen.
With this one now, right?
Yep. Now put it where it was and the way it was. Now remember, the white dot means open space, right?
Right. So
Okay.
I rotate this one?
No, don't rotate it. The way it is. Okay?
Okay.
Because we want to make sure that everything has 8 around it. How many electrons does the oxygen on top have around it?
It has 6, but since we're sharing, there's a total of 8.
That's right. Okay. How many does the oxygen on the right-hand side have around it?
8.
Okay. And then how many how many electrons does the nitrogen have?
Electrons, it has 5, but since we're going to share. What was that? Wait, what was that, Dr. Henry? I heard like a little.
No. You said how many altogether?
Oh, so there's a total of 5 electrons, but since we're sharing, there's 8.
Is there 8? Are you sure? Count them. Count all of the black dots around the nitrogen.
1, 2, 3. We have 5.
Now, not only on the nitrogen card, around it altogether, including the ones that.
So that would include these 2, right?
That's right.
So there would be only the black dots now, right?
Only the black dots.
7?
7, yes. Okay, so my point was, it took us a while to get there, but the point was that since nitrogen is weaker than oxygen. Oxygen is going to make sure that it gets 8 around it, but
Right.
nitrogen is going to try to get as close to 8 as it possibly can.
Right.
And 7 is the closest without going over. It doesn't want to go over.
Right. So how I left it, since I left it like this, it would be better like this or no?
What's that? Yeah,
So this
no,
is how
that's the way
should I
it's
leave
supposed
it?
to be. Yeah, that is the way it's supposed to be.
So I tape it in now?
Yeah, that'll be good. Tape it in and you're good to go.
Oh, is this good how I tape this one in?
Yeah, that's fine.
Okay. Do you want the black dots to keep on showing or cover them?
Yeah, you want them, no, you want them showing so that we can keep track of them all.
Oh, okay.
Yeah, and remember the oxygen technically has a black dot as well that you're not showing because I forgot to put it on there. I mean,
Okay.
the hydrogen, not the oxygen, the hydrogen
Okay then.
on your water molecule.
I just have a question, Dr. Henry.
Yep.
Where did you upload the pictures again so I can print them again? Because on my nitrogens, I just have 5 dots in total.
Okay.
Like missing.
You're missing a few of them.
Yeah.
Yeah. So let me put them, I'm putting them up. Let me fix the ones, I'm fixing them. And so I'll upload them again here in a second.
Okay.
So let me fix that real quick. Sorry.
Yeah, it's okay. And I just got the first.
You say you just got what? You say you just got the first one? Hold on. Let's see.
Mine real quick.
What was that?
Can I show you the one I showed you before that was wrong? I might have it.
Okay.
At least I'm closer, I think.
Sure. Let's
See
see.
something like a.
Okay. Let's see. Okay, that looks good. So count. Do me a favor, count the number of electrons. Yeah, that looks good. That looks good. 2, 4,
I
6,
understand it
8.
now.
You understand
The
it now?
dots were kind of, yeah, they were kind of confusing me at first, but I to make sure to count where they all kind of together will equal 8. Like
Yeah.
all of mine to get credit.
Yep. Yep, that's good. Good job.
Dr. Henry, can you see if my HNO3 is good?
Let me see.
For it's number 5.
Okay.
This is what I have so far.
Okay. Now remember, in this case, your hydrogen isn't going to want to associate with that nitrogen because then that will put too many around the nitrogen. Because remember, the hydrogen technically has a black dot there too. It has a white dot and a black dot.
Right.
Yeah. Okay.
So
so you need to move that one from somewhere else. Now, who's missing a black dot? Looks like you have a couple of them. What was that?
The hydrogen? No, wait.
Well, of course, the hydrogen, but I mean on your other guys. Anybody else missing a black dot?
Me.
You're missing a black dot?
Yeah. Well, on my nitrogens.
on your nitrogens.
Yeah.
I'm fixing that right now. I'm gonna post it up for you in a second.
Okay.
So let me save. So Helen, you're at Harnell, right?
No, West Hills.
I know you where you're at, Alan. I said Helen.
Oh, my bad. I'm sorry. I thought wrong.
Yeah, I am from Harnell.
Okay, so let me put that on Harnell's and then see. But I have to save as.
Dr. Henry, here's my, I don't know if I could do it like this. If you could see it, my H2O.
Okay, hold on 1 second. Let me save this, then look.
Okay, yeah, just let me know whenever you're
Okay,
ready.
no, I'm good now. Show me. Okay, Ellen, you should be able to download it.
Okay, thank you.
Yeah.
Bye.
Okay, that is looking almost right.
Ooh.
Count the number that's around that oxygen. One of the oxygen.
Oh, 1, 2, 3. There's only, yeah, there's 6. Okay, hang on. Oh, I see it. Rip. Okay, real quick, what about, I think I'm good now.
Okay. So.
Oh, wait, hang on. Maybe I jumped the gun. 1, 2. Yeah, it's not?
Okay, let's see. That's 1, 2, 3, 4, 5, 6, 7, 8. And then that's 1, 2, 3, 4, 5, 6, 7, 8. Wait. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So that's 8. And then that's 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 6, 7, 8. 1, 2, 3, 4. So there's something weird. It works. Let me count it again. I'm like, maybe I'm messing up here. So that's 1, 2, 3. Okay, first off. So now the way that you have it, right? It technically works, but does it really work? The way that you have it here, you have a single bond with one extra electron being shared between it. So that's not going to happen the way you have it. So between the nitrogen and that oxygen, where you have 3,
Yeah.
it either has to be a double bond or a single bond or a triple bond. What do you have with? You have 3 electrons that are there. Do you understand what I'm saying?
Yeah, so it can't be the 3. It needs to be a 1. And so you'd almost need to just flip it over. Would it be like flip it to here?
Okay.
Hang on, let me count it. Let's see, I can count it from right here.
How is that working? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Right here.
Okay. 1, 2, 3, 4, 5, 6, 7, 8. That isn't possible.
I just solved some kind of a chemistry math problem right now.
Yeah. Well, well, one thing structurally it won't happen but you just managed to do something crazy. So you see where you have 3 electrons between the nitrogen and the oxygen, right?
Yes.
So that can't happen, right? Because then it's not really sharing. It's sharing 2 electrons, but you have that one that's going to be like a little bit of a radical. It has to be paired up with somebody for it to share. Okay. So that's not going to happen. So you need to figure out a way of making it so that there's 4 in there. The only way that you can do that is if you have, there's ways you can do it. Like if you flip it where you have the double here, that's 8, that'll be 9. Or do you have another oxygen? Oh yeah, you do have another oxygen. Okay, you see where you have your other oxygen, your top oxygen?
Yes, the one I'm holding.
Yep, the one that you're holding at the very top. Okay, so that oxygen, if you flip that one so that it's with the two, just turn it so that the white is right next to the black of the nitrogen. So orient it, just rotate it.
Flip that. So flip
Yep.
the ones with no. Okay.
Yeah. Yeah, I'm like, man, it works, but it doesn't work the right way.
Yeah. Yeah, I see it now. I can.
Yeah.
1, 2.
Yeah, so you have to have even numbers when you're sharing, right? It has to be 2, 4, 6, or 8. You can't have 3. Let's see.
Oh, I just want to make sure if my last two are done, and I'll be done for now. Just making
Okay.
sure. That,
So you have the same problem that he had, right?
right.
Okay. So you need to find, do you have an oxygen that has 2 white dots on one side?
2 dots on one side?
2 white dots on one side.
Yeah, 2 white dots. Well, I used them on this one already.
You already used them on that one?
Oh,
Okay.
but there's one with a positive charge though.
Yeah, that's kind of screwed up, but because it has 6, but it's not supposed to have a positive. You have more electrons. That one's screwed up anyway. So just scratch off the positive because it's not really positive.
All right.
And then use that one.
All right.
Yep.
There's a lot. Have you made mistakes in that type of lab, Dr. Henry?
What was that?
Is that the only mistake you made, or you made several?
Oh, I made a couple. I'm looking at it now. I'm like, man, what was I thinking?
All right. All right. Is this fine? I did it with the pen. All right. So it's ready.
Okay.
I crossed it out with the pen. So
Good. Okay, good. Okay, so now use that one.
and replace it with the.
Replace it with the one that's up top.
This one?
Yep.
Um,
And you want to like
Nope.
this?
The other way. The other way. Okay. So, because remember, you want 8 around sulfur. Count how many you have around sulfur right now.
So you have just sulfur, right?
Just sulfur. Yes.
Right.
But remember, when you're counting both the oxygen parts and the sulfur part.
Okay. So we would have, that would include these two where my finger's pointing, right?
Yep.
Okay, so 2, 4, 8.
Don't count the white ones, just the black.
Oh, okay, just the black only?
Just the black only. Yep.
We only have 6 for the black dots. We have 6 for sulfur, and
Okay.
10. Yep, and 10 for because of the oxygens.
So is it 10 or is it 9?
Ooh, 9.
9. Okay, so then that's a problem, right?
Right.
Okay, so if you look, is it SO42?
No.
For the chemical compound, it's not SO42 or -2.
I guess it's a yes or.
I know I'm asking you. I'm like on the lab. Is it SO4
Oh, yeah.
-2?
SO4
right?
and the -2. Yeah.
Okay, so that's good, right? So that
Right.
means right now you have a -1, right? If you add
Right.
another one, it'll be a -2, right?
Right.
Okay, so then that would give you your -2. So that white dot is really supposed to be a black dot. So that
Okay.
O- can be an O2. It could be an O2-.
Okay. It's
You
just screwed
understand?
up. Yeah.
Well, no, it was not really. It was supposed to be kind of flexible. So, but
Right.
in that case, you want to fill in that 1. because it has an extra electron.
Oh, okay. So I would fill this one in.
Yep, fill in that one, right?
Okay.
Then I want you to count all the electrons around it, because then there's still another issue, right?
Right. So let me fill. So fill in black, pretending like if it was black right here.
Yep. The white one and pretend it was black. Let me fix
All right. All right, I got it.
You got it?
Yeah.
Yeah, I got mine too. I just need to just take these bad boys down. Okay, so I don't know. I don't think I did the same thing, but is it still?
Yeah. Okay, so you got one part right. Now you've got the other side right, wrong, right? Because if you look at it, so in this case, now you have 1, 2, 3. You remember, it needs to be paired up. It has to be multiples of 2. The electrons that are being shared. Is that a multiple of 2? Count the oxygen and the nitrogen that is on the right-hand side.
3, 6. All right, like counting them that are paired.
Yep.
And so pretty much where I messed up is where there's the 3, right? Or like the.
Yep, where you have the 3 electrons. Yep, that's where you messed up.
Let me just get that.
So, but that's only part of it. Part of it is because you have the one that you used, the oxygen that you used. It has one open spot on one side and has an open spot on the other side, instead of having both open spots on the same side. Does that make sense?
So this is what it would end up like this, Dr. Henry? In total?
Yeah, so it's going to be a special case where you're going to have more than 10 around it. I mean, more than 8 around it.
Right.
Okay.
So this one's already fine
wait.
then?
Potentially. But there's also some other things that you've done here, right?
Right.
So like, for instance, you have, let's see. Do you have another sulfur? Let me ask.
Yeah, right
Let
here.
me see your other sulfur. Yes, use the one, that one right there. The one with the.
This one?
Yep, that one. Yep, use that one. Okay, so
Right.
now if you kind of flip it a little to the angle, turn it, rotate the oxygens where the whites are facing the. You see where the white? No, the other way. Rotate.
Right.
Right there. Where the right? Well, no, go back the other way. Right there. Wait, between the two. Yes. So where you see the 2 whites.
Right.
So rotate it a little bit more. You know what I'm saying?
This
2
one?
white dots.
So it's kind of like
No,
this then?
the other way. You want to show the black dots. You don't want to show the white dots.
Oh, okay.
So you see how that it's.
So this is what hide and go seek for the white dots?
Remember, it's an octagon. Yeah, because the white dots are open spots, right? So now count the electrons now.
And for all of them, or?
Yeah, count the electrons. So now the electrons here, these guys really aren't. Let's see, how do I explain this? Really what you want is you want the oxygen where there's 2 dots on one side, not 2 dots, kind of like the one up top. So you want 3 of them that are like that.
Okay.
Okay.
I don't know why this one's like, I completely understand it, but this one's just, it doesn't make, I can't get it to 4. 5, 6, 7. 8, 4, 5, 6, 7, 8. Goes to 9.
So that would be fine, Dr. Henry?
That'll work, yeah, but the two dots here, so the dots that are above it and below it, that technically they should be together.
Okay,
understand?
this one right here?
Yep.
Okay.
No.
So this,
So let's see. Let me see how can I explain this. Let me draw it out. This is the easiest way.
All right.
Share my screen. Okay, so we have the oxygen here,
Right.
and I'm going to use X as S to represent the open space. So you want the open space to be like this. The dots represents the dots. You have
Right.
the oxygen, the sulfur here, where it has its dots.
Right.
And then we have that oxygen that has the extra 2 electrons.
Right.
Okay, so we have this oxygen here that has 6, 1, 2, 3, 4, 5, 6, and it has an open space. Those,
Right.
okay, this guy has 6, 1, 2, 3, 4, 5, 6, and an open space, right?
Right.
But then it's going to be sharing, because these are open spaces, it's just going to be sharing those 2 electrons with the sulfur,
Right.
okay? And then this guy is going to be sharing the 2 electrons with that sulfur. And then this guy is going to be sharing 2 electrons with that sulfur. Whoops. And then this guy okay, is going to be sharing the 2 electrons that were on the oxygen. Okay,
Right.
now the sulfur has 8 around it. Count 2, 4, 6, 8.
Right.
Now your structure, the way that it's drawn, you have an oxygen. Technically, you have this going on. Then you have one that's here and one at the bottom.
Right.
And so you keep the way that it's done. You're doing it so that these guys really should be together over here, and this guy should be an open space.
Right.
Like this. Do you understand?
Yeah.
But you're limited by the number of oxygens that you have and the ones that you've already used, right?
Right.
Okay. So then if you turned it at an angle, then it's in an open space, but you got to remember that these two really belong together.
Right.
Okay. Does that make sense?
Makes sense.
Okay. Good.
So I still have to do any rotations, none of that for that one anymore?
Nope, you're good.
Okay.
You got it.
Just one more and I'll be good for now. And this is
Okay.
for the last one for number 5.
Okay.
This is what I believe so far. Can you see it?
Let me see. Let's see. Let me stop sharing so I can put you as center.
Yeah.
Okay. Okay, so this is another one, the same thing, right? So
Right.
really, it's not going to be this way. You see where that hydrogen is at?
Yeah.
Do me a favor, draw one dot next to that hydrogen. Put in a dot.
Okay.
Yeah. Because
It doesn't matter where?
Put it right next to the empty one.
Okay. A full black dot, right?
A full black dot, yes.
All right. Okay. Yeah, got it.
Okay. So now that guy, now will that match up?
No.
No. So if you turn it to the other side of that oxygen, now does that match up?
Yes.
Okay, there you go.
So that's it.
That's it.
Okay.
Yeah, but just remember that that hydrogen would technically be next to the oxygen.
For this compound, would hydrogen be considered as the
Wait,
extra
hold on.
element added?
Let's see. Hold on. Let's make sure that it's right. So that's okay. So no, it still doesn't work out. Count the number of electrons around the oxygen.
For which one? This one?
For that one's good, right? If you count the one around that, but for the other one, the other oxygens,
The black dots only, right?
black dots only.
6. There's 6 on both of them, so
Are you
there's
sure?
12.
I want you to count again. Not only on the oxygen, but remember the things that they're sharing as well.
Oh, okay. There's 6. 8.
Are you sure?
$10.
Okay, I want you to count one more time. Do me a favor. Now,
Okay,
start with the oxygen on the right-hand side only.
right here. Okay.
So count just the black dots.
Okay, 1, 2, 3, 7.
7. Okay. So does that meet the octet rule?
No.
No, it doesn't. So you need to figure out a way of making it so that it meets the octet rule. So you also we run into the problem that we ran out of your oxygen. So you're, I know you're taping them together, but once you make it,
Right.
take a picture of it and then reuse it. Reuse the ones that are going to be right for it. You know what I'm saying?
Yeah.
Don't dedicate it. Do you know what I'm saying?
Yeah.
Okay. I'm going to try to fix that for the next set. So.
And here, real quick, just so I can mark it off. Here's my. Is this my H2O? Yeah, H2O.
Okay. H2O. That looks good. Yeah.
Okay. So I got the 2, and I'm still. I don't know why I'm having so much hassle with the NO2. 1, 2, 3, 4, 5, 6. Like this is not right? Like we could.
Okay. Is it? You tell me.
I don't think it is.
You're right. It isn't.
Like
Why
there's
isn't it
one.
right?
I know that's why, because the only way I feel like I keep trying to get it for it's right is when it's has the 3 on the one. Yeah, because there's only 7. Unless I go, what if I do 1, 2, 3, 4, 5, 6, 7? Now that makes it 9. Oh wait, unless I get a different oxygen. Oh wait a second. Here. What about that?
Let's see. That's 2, 4, 6, 7. Okay, so does that work?
Yeah.
How about you
I mean,
flip
wouldn't
one
it-
of those oxygens? Because I know you don't have the right oxygen with it. So flip one of your oxygens. Let me see your oxygens. Lift it up again. Okay. Okay, so we have 2 empty spots on the nitrogens. So if we flip that one oxygen, that gives us 6. That doesn't work. Actually, no, it will work. Hold on. Go do me a favor, lift it up one more time. One more time. Okay, so you see where your oxygen is at? Let's see. 2. Yeah, you have the same problem. What do we need to do? 6. Do you
Yeah,
have
I've got
an
all the
oxygen?
other ones pretty much.
What was that?
So you just think I have the wrong. I'm just playing around.
So do you
with
have an
rows of
oxygen where there's
oxygen.
just 2 white dots on one side?
Yes. Yeah, let me see if I can just get it without 4, 5, 6. So like this one right here.
Yep. Use that one.
Okay, I'm just trying to see. I still run into the same like. If you put these two.
Not there, but don't put it there.
1, 2, 4.
Don't put it there. Put it on the other side. On the
Oh,
other
to
side
make
of
it.
it.
That's 9, right?
Not if you put it together, right? It's 9 if you put it together, but now, okay, now turn it. Turn your oxygen. Turn your
Turn it
oxygen
to.
the other way. Keep turning it to the open spot right there. Now do me a favor, count it now.
Seven, 4, 5, 6, 7.
Okay, you have 7 around the nitrogen. How many do you have around the oxygen?
8.
You have 8, right? And around the other oxygen?
Okay, so
yeah. Okay,
8.
now, so here's the secret. Anytime that you have an odd number of electrons total, like all your total electrons, you have a total of 17 valence electrons, you're never going to be able to reach your octet. So you want to make sure that the one that is the most electronegative, or the one that's closest to the noble gases, reaches its octet first, and then the other guy that's further away, they can get as close to the octet as they can get, right? You want to get to 7 without going over, right? In the case of nitrogen.
Okay, I see.
Okay.
I think that was my problem. Is I was trying to get them all to be
the same. Yep. I figured that after.
I think I showed you. I think I've showed you all of them. I think. What would I be missing?
Dr. Henry?
Yep.
Let's see. So basically what I just showed you with the, let me see, with HNO3, was it only from thinking about replacing the nitrogen, what I was thinking about right now, or basically I was done with it?
You were pretty much done with it. I mean, all it was that, if I remember correctly, is that one oxygen. You wanted to use a different.
Right.
Yeah.
Okay, then. So basically I was pretty much done with it.
Yeah.
So I have one more question about this lab. For question number 1, it's only talking about the single element. So you just want the number of their valence electrons, from what I read from it?
Yep.
Okay, then. Well, Dr. Henry, well, thank you for your help again. So.
Hey, that's what I'm here for.
Yeah. Well, thank you. So.
You're
if I have any.
Good. So do I have to send?
What was that?
You can go ahead. Do I have to send you pictures of these, or?
It's good to take pictures of it. You want to put it in your lab report. So just take pictures of them and put them in your lab report. You don't have to, because you showed me them, or you could just tell me that, hey, we looked at it during this day,
Okay.
You showed me them, but me,
okay,
so
I can just say like that we did it, that I showed you. Okay.
Yeah. But if it were me, I'd like to have a record of it. So then that way, if it happens to fall up on a test or anything like that, then I have some images already. But that's just me,
All righty.
All right. Well,
thank you.
Okay.
Okay.
You're welcome.